Good morning, everyone. We will start the technical program. Today, we are honored to have with us Professor Dr. Onur Mutlu from ETH Zurich. Onur Mutlu is a professor of computer science at ETH Zurich. He's also a visiting professor at Stanford University and a faculty member at Carnegie Mellon University. His current broad research interests are in computer architecture systems, hardware security, and bioinformatics. We can say that he has invented over the years many patents that have influenced and been employed in commercial microprocessors and memory storage systems. He holds a PhD and a degree from the University of Texas at Austin, USA, and the Bachelor of Science degrees in Computer Engineering and Psychology from the University of Michigan, Ann Arbor. Yeah, we can say a lot of things about he's currently also leading the Safari group in ETH Zurich, and as I said, we are very honored today to have him with us. He will talk about the memory-centric computing. Please, the floor is yours.
Thank you very much, Slavisa, for the kind introduction. And thank you very much for being here early in this coldish morning. Well, the lights are actually a lot. Maybe if there's a way to reduce them, that'd be good. But I'm going to talk about, this is my first time in Nancy, so it's nice to be here. Thank you for the invitation. I'm going to talk about memory-centric computing. This is an area that we've been working on for a while now, and I think it's an exciting area because of the promise it brings to greatly improve performance, efficiency, and sustainability of computing systems going into the future. So let's get started. Today, computing is bottlenecked by data. A lot of workloads are all data intensive. Clearly, we're seeing this in machine learning, but increasingly, we're going to see it in many other domains, like genomics is already happening. And I believe it's going to be one of the next biggest killer applications in the world soon, different types of omics as well. These workloads require rapid and efficient processing of large amounts of data, and data is increasing on top of this. We can generate more data than we can process, and we need to perform more sophisticated analyses on the data. This is an example from the CTO of a company who are building chips that are this big. These are wafer scale chips. And the reason they're building chips that are this big is because memory model requirements are growing exponentially, while training requirements in terms of computation are also growing exponentially in very large networks, machine learning models today. And they would like to put a lot of memory and computation together in this large chip. I will argue that this is too small because especially with the technology that they're building this chip, SRAM, this is going to be very hard to scale, but we can have a discussion about that. The good news is one of the applications that's driving this sort of designs is growing significantly. There are other applications. It's not just machine learning. Even though machine learning is very interesting, there are many other applications that are actually maybe even more interesting and maybe even more sophisticated than machine learning. Genomics is one. We can actually generate a lot of data because technology has enabled us to sequence genomes very efficiently at high throughput and low latency at low cost using devices that look like this. Essentially, data is exploding in this area also. We do a lot of work on genomics. I'm not going to talk about that, but one of the uses of memory-centric computing, both memory and storage-centric computing, is actually to process genomic data in a sophisticated manner. And there's a lot that goes into genomic processing. Machine learning is actually a part of genomic and data analysis, but there's a lot more that happens here. I'd be happy to talk separately. Maybe I'll flash some papers later on. In my opinion, we actually have a bigger responsibility into the future. As computing scientists and engineers who actually design computers, we build infrastructure. And the infrastructure we build is going to be used everywhere. And this infrastructure, if it's not efficient, if it's not robust, if it's not high performance, it's going to cause a lot of problems. Basically, we have a responsibility, and I'd like to summarize that responsibility with pictures. Do we want a world that looks like this, or do we want a world where we cannot breathe in? As human beings, I think we've always been greedy. Hopefully that greed takes us to better places and not worse places. But if we want to design computers, I think we would like them to be high performance, energy efficient, and sustainable, all at the same time. We don't want to go into a trade-off where we improve performance but waste a lot of energy, which is what's happening today, where we improve performance but waste a lot of sustainability, which is really what's happening today. I believe partly because we actually don't do the right thing when we're designing our computers from the fundamentals. So we really want to improve all of these at the same time. And today, sustainability is actually a big issue. And I think we're wasting a lot of hardware unnecessarily because we're actually trying to tolerate the long memory latencies that I will discuss soon. And hopefully I'll give you some examples of that also. Basically, in most of today's applications, data access is the major performance energy bottleneck. And fundamentally, the way we design our computers, we actually don't treat this right, meaning we cause a lot of energy waste because we move data from wherever we generate the data, and then to the storage, and then to the memory, and then to the SRAM on chip, and then to the registers, and then finally to the computation units. This data movement back and forth and back and forth and back and forth caused a lot of energy waste. At the same time, it caused a lot of performance loss. Now, we recognize the performance loss. We actually make our systems extremely complex to overcome the performance loss due to data movement. We actually built very sophisticated memory hierarchies, levels and levels of caching, levels and levels of prefetching, levels and levels of address translation to access the memory hierarchy, large out-of-order execution engines to overcome the effects of data movement, and also heavy levels of multi-threading. These happen both in hardware as well as software. So our systems are very complex to tolerate this data movement. And sometimes these techniques work. Many times these techniques actually don't work very well. They're extremely inefficient. If you look at caches, for example, more than 80% of the data that's inside a processor's caches are not used. So we waste a lot of area for that purpose. And this complexity, this added complexity actually turns back on us and actually reduces performance as well as increases energy. So we're in the vicious cycle right now. In this vicious cycle, we're wasting energy by moving data. To tolerate the performance effects of that data movement, we actually waste more energy by making our systems more complicated. And I think we need to break this vicious cycle to make our systems fundamentally efficient. Basically, the problem is today's systems are very processor-centric. All data has to go into the processor at great system cost. And it's not just the processor, it's really a small fraction of that processor, as you will see soon. This is my cartoonish picture of a processor. I actually drew this picture in 2008 when I wrote my first proposal to the National Science Foundation when I was at Carnegie Mellon University. And the picture didn't change that much, but I think there will be some interesting things that are happening today that were not happening in 2008. Hopefully, I will give you some examples of that also. Essentially, if you look at this picture, only the cores or accelerators are the ones that can process data. Everything else in the single node system is there to store and move data. Caches, interconnects, other caches, other interconnects, memory controllers, other interconnects, memory, other interconnects, storage, other interconnects. If you do the computation, more than 90% of a single node is really dedicated to moving and storing data. Now you take this picture, you go in front of a 10-year-old kid and ask the 10-year-old kid, I'm dedicating almost all my resources to storing and moving data. I should not have a problem with the storage and movement, right? That's a leading question, of course, but probably the 10-year-old kids would say, no, you should not. You're putting all your effort over there. You should not have a problem there. Yet, our systems are still bottlenecked by memory. So I think going forward, we really need to think like the 10-year-old kids. We need to think about our computing systems as a blank slate. And we should think about how to design our computing systems fundamentally from the ground up so that we can get performance, energy efficiency, and sustainability all at the same time. Okay, let me give you some examples. This is not my picture. This is AMD's picture. And if you look at this, the green box over here is L2 and L3 caches. This is not all of the data storage and movement units. There's a global memory interconnect over here, which is huge. And there are L1 caches, registers, etc. And I have not even shown you the DRAM and also the storage. So if you don't like AMD, AMD is actually putting more and more, with very interesting technology. We're putting actually 3D technology on top of a processor chip. You can put a cache chip, but that's more and more caching, essentially. It's more of the same thing. Should we do business as usual, or should we rethink our architectures differently so that we can do more with this three-dimensional technologies? If you don't like AMD, this is IBM. It's essentially the same story. If you look at this is L2 and L3 caches, and there's a lot of interconnect communication interfaces that are outside the chip. Most of the chip is really storing and moving data. This is another system that may be in your pocket. and you have a chiplet of SRAMs, mostly SRAMs, and then there's DRAM, and then there's the darkness, which everybody forgets about, which is really storage. So now I'm going to give you some numbers very quickly to show the impact of the problem. We've always known that memory is a problem and data movement is a problem. This is one of my favorite articles from 1990s. It was written by Dick Seitz, who was the chief architect of Alpha processors. Alpha was the company that was competing with Intel. They were building some of the fastest processors of their time. And he was the chief architect. After his team designed one of the fastest processors of its time, Dick Seitz wrote this one-page article, which I would recommend everyone to read. And in this article, he says, we designed this beautiful processor. It's capable of finishing 4 alpha instructions every clock cycle, which was a very fast clock cycle at the time. Unfortunately, on this important workload that we believe we designed this processor for, it's a database, commercial database workload, it finishes 1 instruction every 4.7 clock cycles. So it's operating at about 5% of its efficiency, peak efficiency. And he basically concludes the article. He says that this is because it's waiting for data to come back from memory. And he concludes the article with this sentence: I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. Okay, this is him. Fast forward about 10 years. This is data from my own PhD thesis. We worked together with Intel to actually understand the effect of different workloads on the design of future processors that they were designing. And we found essentially the same thing. On most of the workloads, the processor waits for data, and it doesn't do useful work for most of the time. Okay, you don't believe Dick Seitz, you don't believe me, since everybody believes Google today. This is data from Google in 2015. They essentially repeated a similar study on all of their data center workloads, and they basically showed that on all of their data center workloads, the processor most of the time waits for data. It's actually completing instructions, doing what it's really supposed to do, only 10 to 20% of the time. Again, let's think like a 10-year-old with a blank slate. I'm given this system. This system is doing what it's supposed to do only 10 to 20% of the time. Is that a good system? I would argue not. Okay, so that was performance. Let's talk about energy. Energy is much worse. And we don't normally think about energy. When we design processors, it's really performance first, energy next. We should change that mindset also. But essentially, this is data from Bill Daly in his high-peak keynote in 2015. You can argue with all of these numbers over here. What remains is memory access is much more costly in terms of energy compared to a complex arithmetic operation. This is a floating point operation. And the disparity is between 100 to 1000x. It's very difficult to get it down below 100x. Now, it's good to ask the question over here. If I'm doing a complicated arithmetic operation, does it really make sense to do 2 memory accesses, assuming it has 2 operands, to bring the data into the processor and then write the data back to the memory one more time? So 3 memory accesses for an arithmetic operation. This is an optimization problem, of course. Sometimes it makes sense. It makes sense when you can actually overcome or amortize the cost of energy that you spend to actually bring the data and write it back. And you can figure out whether that optimization makes sense. And it depends essentially on the locality of the applications. And many applications, you don't have that much locality to overcome the energy cost of memory access. Okay, that was a complex arithmetic operation. Let's talk about a simple arithmetic operation. It's a 32-bit addition and a memory access. The disparity increases to 6400x over here, according to those numbers. Today, people are trying to reduce the width of computation, which is, I think, great, so that we can actually be much more energy efficient. But as you reduce the width of the computation, the disparity between computation and memory also increases even more. And we're not even talking about storage yet. If you actually talk about the energy expended on a storage access, add another order of magnitude over here, and the numbers become crazy. Basically, we're expending 64,000x. I just made up that number, but it's close, to access data from storage and bring it all the way to the processor. Okay, to overcome that, it's very difficult, actually. Most applications don't have that much locality to overcome 64,000x. That's why I say we forget about storage. Okay, so we did a lot of studies to quantify the energy impact of data movement. I'm going to give you very quick results. With Google, we studied common applications that people use on their mobile phones. For example, TensorFlow inference engine, Chrome browser, YouTube video encoding and decoding. And in common cases, we found that more than 60% of the total system energy is spent on data movement. This is common case. In worst cases, where data is a lot more, you get closer to 90, 95%. We repeated the study more recently. We looked at edge machine learning accelerators that Google uses in their phones. And we wanted to understand the energy impact, energy inefficiency in them. I'm going to talk about this a little bit more. But the key takeaway is that in large machine learning models that are executed on the edge to do inference, more than 90% of the total system energy is spent on memory. This is just a very quick, brief overview of one of the studies that we did. If you look over here, we look at long short-term memories and transducers, and most of the energy is really spent on off-chip interconnect and DRAM, even with a lot of optimizations. Okay, so basically the fundamental problem is processing of data today is performed far away from the data. We're moving data all around. I believe to solve this problem and to achieve a much more sustainable, efficient, and high-performance future, we really need to enable computation with minimal data movement, compute where it makes sense, where data resides, as opposed to only in the processors. And we want to make computing architectures much more data-centric. So if you look at an SoC today, there are many places where we can do computation. We're limiting ourselves to a very small fraction of this SRAM-dominated chiplet, but everywhere else is dark. But we can actually enable computation everywhere else, as well as on all parts of this chip over here. And maybe if we do that, then we can reduce the complexity that goes into our systems so that we don't make the processor chip bigger and bigger and bigger and more complex. Okay, so there are a lot of ways of thinking about this. I think in a longer term future, this is actually the paradise of distributed computing. So every part of the system is a distributed agent, and they communicate with each other to solve a problem. I'm not going to go there. I'm going to still use existing paradigms and talk about memory as an accelerator. So today we know how to build accelerators to make computation much more efficient. We've been building a lot of accelerators in addition to general purpose processors. We're going to look at building accelerators on the memory side so that we're less bottlenecked by memory. And then the question will become, what do you execute on the memory side? There are many questions over here if you start doing this. I'm going to focus especially on main memory, but I'm going to very quickly talk about storage as well. I believe these are actually very similar things, except design trade-offs may be a little bit different. We're going to enable the main memory to compute, and processor or accelerator may ask the main memory, can you compute with this function or this application for me? And the memory will say yes or no, and then return the results. Even with this accelerator-based paradigm, there are many questions. How do you design the compute-capable memory and the controllers? How do you design the processors and communication units and then change them maybe over time? How do you design the software and hardware interfaces to enable this sort of computation in memory? How do you design the system software compilers and languages to actually enable this for the masses so that the programmer doesn't need to deal with a lot of the complexities? And then how do you rethink the algorithm so that it can actually fit the devices underneath? I've also mentioned that theoretical foundations over here. If you've taken a computing theory course, computing theory is extremely processor-centric, meaning when you quantify the complexity of an algorithm, you think about operations. How many operations in an order of magnitude basis does this algorithm do? And that's algorithmic complexity for us. But maybe that's not important because we're dominated by so much data today that maybe we really should be focusing on developing a theory of computing that's data-centric. And I strongly believe in this. So in the end, we're going to focus on across the stack design. And there are exciting problems across the entire stack that touches everything. This doesn't mean that this cannot be adopted by changing small things within the stack. And I believe we really need to think about how to take it step by step. But over time, I think the change to a data-centric paradigm will happen by re-examining the entire stack. Okay, so I should also say that we're not the first ones to talk about it, clearly. There are many smart people who have developed computing in the 1950s, 1960s. And these are the earliest papers that I could find on this topic. These folks called it logic in memory. This is going to be an example of what I'm going to call processing near memory. I will use processing in memory as a general term because they use logic in memory, which is processing essentially. And then there are other works also from Harold Stone, for example, who has a beautiful textbook on high-performance computer architecture. If you're interested, you can read these papers. You may ask, these are 1960s. What has changed? I've already told you what has changed, actually, from the applications of system size. Today, basically, we want performance, energy, and sustainability, and we can improve all metrics by minimizing data movement. That was not the case for a very long time, even in 2010s. I will also say something else, which is about memory technology, and I will kind of have a detour for memory technology, because we're having a lot of trouble in memory technology today, and we never had this much trouble with memory technology. Technology scaling is actually not going well. Some people may say it's close to ending. And we have a lot of scaling issues, and they demand intelligence in memory. They actually demand computation capabilities on the memory side, and DRAM vendors are actually implementing that today. Even though if you went to them 10 years ago and said, I want computation on the memory side so that you can actually scale your memory, they would kick you out of the room. So basically today, things are happening on the technology side. And there are also emerging technologies that can enable new functions in memory. I will very briefly talk about that, especially 3D stacking technologies. So basically today, I don't think we have anywhere to escape. Applications and systems are pushing us to do something different. And memory technology is pushing us also to do something different. And systems are really in the middle today. So let's talk about this memory technology a little bit. I call this technology push toward memory-centric computing. And I'll give you a couple of quick examples on the topic. I'm going to talk about RowHammer problem. This is an area that we have worked on for more than a decade now. But essentially, what is technology scaling? Technology scaling is you reduce the size of a circuit. It could be logic, it could be memory. And as you reduce the size, you gain benefits. In terms of memory, you get capacity benefits, energy benefits, latency benefits potentially, usually not as much, but definitely capacity benefits. And as you reduce the size of the circuit, memory cells become smaller and memory cells become closer to each other. And unfortunately, this causes robustness, reliability problems. And we have shown that you can predictably induce bit flips in commodity DRAM chips, which should not be happening. You should not access memory and cause a bit flip, cause data corruption essentially. And essentially, all recent DRAM chips are fundamentally vulnerable. And this is a robustness problem which affects reliability, security, and safety. And what is exciting, especially to the security folks, is that this seems to be the first example of how a simple hardware failure mechanism can create a widespread system security vulnerability. That's why people are writing articles that look like this. I like this one a lot, actually. It says, forget software, now hackers are exploiting physics. And this is actually enabling people to look more and more in the underlying workings of hardware, people who have normally not looked at the underlying workings of hardware. So let me give you the quick idea of what's happening so that hopefully we can appreciate the issue. So basically, if you look at memory, memory consists of two-dimensional arrays of cells. This is DRAM, rows of cells and columns of cells. If you want to access some data, you need to activate one row, which means that you need to apply high voltage to the word line, that actually connects all of those cells to the corresponding bit lines. Now, if you want to access something else, you apply low voltage, you close this row, and then you open another row. Now, if you keep doing this repeatedly, activate, precharge, activate, precharge, activate, precharge, high voltage, low voltage, high voltage, low voltage, high voltage, low voltage in DRAM, the perturbations that you cause because of the toggling of the word line cause data leakage, charge leakage on some vulnerable cells. And if you do this enough times before the cells get refreshed, some fundamentally vulnerable cells actually flip, meaning they lose their data, they get corrupt. Clearly, this should not be happening, right? We're just accessing memory. We're not even writing anything to memory. We're just reading from memory. So we should not be corrupting data. These corrupted cells may belong to some other application. They may belong to the operating system. They may belong to actually some really security critical data. So we call this the hammered row. We call it the victim rows. And we essentially show that this happens in most real DRAM chips you can buy today. And we've done a lot of work in this area. I'm not going to go through this. And this is a technology scaling issue. It's happening because cells are small and cells are close to each other. They cannot have enough charge. And whenever you actually perturb adjacent cells, charge in adjacent cells actually gets drained. And we have shown that the number of activations you need to do to induce a bit flip in an adjacent cell has reduced by more than 100x in a decade or so. So today you can actually induce these bit flips after, let's say, 300, 400 activations, which is fascinating to me. So we're pushing the limits of technology so much that cells are actually not becoming reliable. So we have written a lot of papers. I'm not going to talk about that, but other people have actually done a lot of work on this area. They replicated a lot of our results. And they basically showed in the security domain, one can exploit these bit flips to take over a system using a user level program. You can read data that you do not have access to. You can break out of virtual machine sandboxes. You can corrupt some important data, for example, weights in machine learning models, and machine learning inference may become useless because your accuracy goes down significantly. Or you can steal secret data like cryptographic keys or machine learning model parameters. So this should not happen. And there's a lot of exciting work in this area. I will end the security part with a quote. This is a quote from a famous hacker. He says, RowHammer is like breaking into an apartment by repeatedly slamming a neighbor's door, until the vibrations open the door you were after. So if you're actually stuck in this room, in this beautiful auditorium, don't worry. Keep banging on the walls. And if the RowHammer is in effect, maybe a door will magically open. It's kind of like that. Okay, so there's more work in this area that I'm not going to talk about, but I'm going to say what is the solution to the problem. You can understand the problem, you can do a lot of testing. The solution in the end, we have always argued that you need intelligent controllers. This sort of technology scaling issue is very, very difficult to solve if you don't build an intelligent controller that protects the memory. And that intelligent controller's job is to really understand what's going on in the access patterns, do some computation on the access patterns, and prevent this sort of bit flip. And we've written papers to argue this even before we exposed RowHammer. And finally, about a decade later, industry is picking up on this in a major way, I would say. This is the first paper from a major DRAM manufacturer in ICECS published in 2023 that acknowledges the problem and that describes that they're essentially building a memory controller inside the DRAM chip to solve this problem. The idea very quickly is inside the DRAM chip, they have counters to keep track of number of activations to each row. And these counters are monitored periodically or once in a while. And if the counter is greater than some value, some mitigating action is taken. They don't tell exactly how they do it. There's some computation that happens over here. So they actually still resort to some security by obscurity, which is not a good thing, but we can discuss about that also. But the good thing is they're putting computation inside the DRAM chips. This is not a cheap solution. This is a costly solution. And it is adopted by JEDEC in DDR5 standard very recently in April 2024. So everybody's going to be building these controllers inside your DRAM chips very soon. The question, of course, always to ask is, are the solutions good? So you can build a solution so that people don't cross that fence, but people figure out how to cross that fence easily. So we have recently shown that there are other effects that are technology scaling problems. This is row press. And the idea over here is you don't need to keep the row activated many times before you can actually induce these bit flips. If you open a row, if you keep it active for longer, you can actually reduce the number of activations that are needed to induce a bit flip. And this actually bypasses a lot of the solutions that are developed in industry, and it has to be taken into account. I'm not going to go through this in any more detail, but this shows that there are more effects coming over time to really put more complexity to our memory controllers to fix the problem. There's actually more in one of my students' PhD thesis that was defended very recently. If you're interested, this is one of the state-of-the-art works. So I believe there's more to come, and we're going to keep adding more and more complexity to our memory controllers, add more and more computation to memory controllers to actually solve these problems. I liken this to flash memory. If anyone has done work on flash memory here, they know that flash memory cells off the bat don't work. Most of the cells are actually very unreliable. What makes flash memory really work is a controller that really understands the characteristics of the cells and that changes the voltages, adjusts the ECC, error correcting codes, and does a lot of other tricks to actually make things work. And I believe in DRAM, we're going to see more and more. So we're going to put more computation capability on the DRAM side as well. Computation capability already exists heavily in the flash side. So I believe actually doing computation near flash is a very good idea. And we have some works, but I'm not going to talk about that today. So you may say that, okay, you're old or something, or maybe you're not looking into the future. There are emerging memory technologies that are going to solve a lot of these technology scaling problems. I agree, they need to be investigated. And we have actually done a lot of work in this area also. But unfortunately, there's no memory technology that doesn't require this sort of controller. We've looked at phase change memory and STT-MRAM, for example, for a long time. And all of these memory technologies have endurance issues or other types of reliability issues that necessitate an intelligent controller that does computation. And when you actually scale a lot of these technologies to very small node sizes like we're seeing in DRAM today, you're going to see even more issues like write disturbance, read disturbance, that will be very similar to what we're seeing in DRAM. Okay, so I've kind of motivated right now that we're kind of squeezed in the middle. Hopefully I've convinced you that we have nowhere to escape. Now let's take a look at how we can solve the problem with some example ideas. I'm going to call the general approach processing in memory. And I think fundamentally there are two types or two approaches to processing in memory. One is processing near memory, which is what we're doing today. The other is processing using memory, which is more fundamentally different, let's say. So what is processing near memory? Processing near memory is essentially what we're doing today. You have logic, you have memory, you design them completely separately, you have some interfaces, and you decide how close that logic is to the memory. Today, we're quite far. You can make it even farther, or you can make it even closer. So you put the logic closer and closer and closer to memory in the controllers, inside the DRAM chip, next to each subarray, next to each row buffer. But logic and memory are still separate, but you can actually use that logic. So it doesn't change the paradigm as much, although it has some adoption issues as we will discuss. And this can actually enable much lower energy, lower latency, and high bandwidth access to large amounts of memory. So that's easier to do. And I'm going to talk about that first. I'm going to go through that relatively quickly. And this is what's happening in industry today. Industry is actually picking up on this. Processing using memory is fundamentally different. You have logic, you have memory. Forget about logic. We have only memory. If you look at memory, any memory has some fundamental capability to perform analog computation with its operational characteristics. We're going to exploit those operational characteristics to do computation without adding any logic. And that actually is fascinating because we actually have some real results from real DRAM chips and flash chips that show that they're capable. And there's more, of course, emerging memory technologies. But of course, I'm not going to argue that these should be done separately. I believe we need to actually do both to get to a much better level. So we need to use processing near memory and using memory at the same time. So the good news is industry is picking up on the easier part, which is the processing near memory part. We have three-dimensional stacking technologies that are going to be better and better. And we can actually put computation in the logic layer on the memory layers. I'm going to talk about that in the soon. But there are also other companies like UpMem, which is a startup in Grenoble in France, which has put general purpose processing units next to each DRAM bank. And we have actually done a lot of work with their chips. We have a lot of publications that I'm not going to talk about, which is fascinating, I think. But also large manufacturers like Samsung, SK Hynix, Alibaba are picking up on this. And they're actually putting next to each DRAM bank, they're modifying DRAM chips. And next to each DRAM bank, they're putting accelerators that can do matrix operations. There are also other forms of processing near memory where you can actually design a board that looks like this. And you can have an FPGA chip that is connected to many memory chips over here. And that FPGA chip, you can do reconfigurable computation. In this particular case, Samsung and Meta did recommendation inference computations. So there's a lot that's going on in industry today. And I'm not even showing experimental chips and startups over here, which are many more than this. And then we actually have the right movement and interfaces in industry. We have this compute express link, for example, that enables offloading computation to outside of a processor or an accelerator chip more efficiently. So you can do computation anywhere outside of the chip, which is good. So these are actually good directions, in my opinion. Now, let me give you some examples of our results in the area. I'm very interested in actually emerging technologies like 3D stacking. And I think 3D stacking enables us to do computation very closely, tightly coupled with memory. So you have a logic layer underneath memory layers, and you have many connections between the memory layers to the logic layer. Depending on the maturity and advancement of the technology, the connections may be very, very high bandwidth or relatively low bandwidth. But this logic layer, if it's a quality logic layer, you can actually put anything on there, limited by the thermals, of course. And in this logic layer, you can have low latency, high bandwidth, low energy access to the memory layers. And I believe other true three-dimensional technologies like monolithic 3D stacking are under development, and there will be more in this area. So when we first started looking into this sort of technology, we said, what can we do? What kind of application can we redesign to take advantage of this technology? And we immediately looked at graph processing, because graph processing is very much bound by random accesses. Memory hierarchies don't work well with graph processing. So what we designed is something that looks like this. I'm not going to go through this in a lot of detail, but essentially you can think of this as an accelerator where you offload your graph computation into. It's kind of like a primitive GPU. And in this accelerator, you have a two-dimensional array, a distributed system of these three-dimensional memory plus logic chips. Each memory plus logic chip in the logic layer has many processors. We added in-order cores, very simple in-order cores. These many processors can communicate with each other to actually perform graph computation. And what we do in this chip is to move functions to the data, as opposed to data to the functions. This way, graph nodes are partitioned across these in-order cores. And whenever a core needs to update a graph node, it sends a message to the core that houses the data on top of it. So it's programmed using message passing, remote procedure calls, just like a lot of data center systems are programmed today. And we actually add a lot of prefetching mechanisms to take advantage of the high bandwidth. I will not go through the design details. They're all in the paper. It's about 10 years ago. But at the time, we were able to provide 8 terabytes per second access to 512 in-order processor cores. And you can see that the system looks very different. These are all processor-centric systems. You have the processor-memory dichotomy. In Tesseract, you have a distributed system of memory-centric systems, essentially. And this sort of system enables significant performance improvements. Our results show that you could actually get more than 13x performance improvement compared to state-of-the-art graph processing algorithms. Later works actually improved that. They made it closer to 100x. And the energy reduction we showed was about 8x, and later works actually improved that also closer to 100x. So with this sort of customization, you can actually reduce the energy by 100x while also improving performance at the same time by 100x. Other works actually customize to graph processing much more. And this work, if you don't have time to read the full paper, we have a 2-page retrospective that is selected to 50 years of ICECS. That was last year. So there's more to do in this area. I think graph pattern mining is also interesting. I'm not going to talk about that. If you actually rethink your algorithms completely and rethink your instruction set architecture to make it much more set-based, and also rethink the hardware such that the hardware can actually accelerate the sets, this is the sort of work that can actually improve things a lot. And we looked at a lot of graph processing algorithms through algorithm, ISA, hardware co-design. If you're interested, you can take a look at it, and you can get even more performance improvements that way. I will talk about something that's, let's say, less changing to the entire system. I'll talk about accelerating neural network inference. This is one of the works that I mentioned that we did with Google before I moved to processing using memory. So in this work, very quick summary, and then I'll go through that also relatively quickly. Essentially, we analyzed 24 edge models from Google. These are proprietary models that are used in the field. And we found out that the edge tensor processing unit is not good at handling essentially memory access. It's a monolithic edge accelerator. And this accelerator is actually very inefficient, as I will show you. And the main reason is it tries to do everything with one processor. Whereas if you look at the models that are being executed, there's a lot of heterogeneity across the models, heterogeneity across the layers in terms of compute and memory requirements. So the proposal that we have is actually a heterogeneous accelerator that consists of both compute-centric and data-centric accelerators, and a scheduling system that schedules computation on top of different accelerators. And if you actually do that, you get about 3x performance improvement, about 3x energy improvement, while also reducing the area that's dedicated to the monolithic accelerator. So a single monolithic accelerator that tries to do everything is actually more area costly than, and also lower performance and lower energy than 3 different accelerators that are simpler. Okay, I'll go through this relatively quickly. Essentially, this is what we observed. There's significant variation in terms of layer characteristics across the models. This is parameter footprint, how large the parameters are. You can see that there's a huge variation over here between different LSTMs, for example, have very large parameter footprint, whereas some CNNs have very small parameter footprint. And this is arithmetic intensity on the y-axis, and there's a huge variation over here as well. And there's also diversity within the model. Within layers of a single model, you have a huge variation in terms of multiply and accumulate operation intensity as well as arithmetic intensity. So the idea here is to exploit heterogeneity. And we have a runtime that schedules different layers to different families of accelerators. And you can see that one of the accelerators is CPU-centric or processor-centric, and the other 2 accelerators are memory-centric. They're in the logic layer of 3D stacked DM. And we're going to offload layers. We're not going to offload an entire machine learning computation. Extremely compute-intensive layers go to something that looks like the current HTPU accelerator. Now, how do you identify lever families? Essentially, you need to do profiling. I'm not going to go through this in detail. But in the end, if you do the profiling and scheduling, you get significant performance energy improvements, especially on large models over here. But on average, you get about 3x energy reduction. On large models, that's closer to 5x or so. And again, you get throughput improvements, especially on large models, but also on small models as well. Again, I'd be happy to talk about this. We don't have a lot of time, so I'm not going to go through this in detail. But there are also papers that we have written in the topic. We have also written papers on mobile workloads that I'm going to skip. I will very quickly mention that this is memory. If you actually extend this to the storage system, the opportunities increase, in my opinion. Because if you look at a storage system today, storage system is a system by itself. We have the system, and then we have the storage system. Storage system is really a small system that has its own CPUs and accelerators. Then why don't we forget about the system and use the storage system to actually do the computation? And that's the idea over here. In genomics, for example, some workloads are so large that it makes sense to actually keep them in storage. And we've shown positive results in genomics, especially metagenomics, but I don't have time to talk about these. Because I will talk about something else, which is processing using memory in the remaining time. But if you want to see many more examples, we have an archive paper on this topic that we keep expanding. This is overdue for expansion, so we're going to put out another release that covers more recent work in the last year. Now let's talk about processing using memory. Processing using memory is fascinating from my perspective, but I'm going to look at a specific form of processing using memory, which is processing using DRAM. Basically, I'm going to show you that we can natively support bulk bitwise operations in DRAM and or not majority nor NAND, copy initialization, true random number generation, physical unclonable functions. And you can do more complex computation using lookup tables. You can do this mostly at low cost. I'm going to give you some examples. Essentially, the idea is to use analog computation capability of DRAM cells, but also the digital to analog and analog to digital conversion capability in the sense amplifiers. So it's not pure analog computation, which has a lot of issues, in my opinion. But inside the DRAM cells, you already have digital to analog and analog to digital converters, because DRAM fundamentally has a digital interface, right, so that we can actually access the data when we actually read a cell. So the basic idea that we're going to exploit will be activating multiple rows to perform computation, either consecutively or in parallel. And the real fascinating thing to me is that this works even in off-the-shelf commodity DRAM chips. You take a DRAM chip today, it's not designed for this purpose. No DRAM manufacturer will advertise you that their DRAM chips can do computation. We actually show that by changing the memory controller, by violating the timing parameters, you can get all of these functions. And you get significant performance and energy improvements, as we will see. So before I delve into computation, I will talk about something that's very simple. And I think we need to think simple going into the future. There are some simple functions that we treat very badly in our systems. One of the examples is data copy and initialization. There's a lot of applications that do data copy and initialization. And Google, in their paper that I mentioned earlier, showed that about approximately 5% in their entire data center cycles is spent only on two functions, memmove and memcopy, essentially moving and copying data. Now, how do we do data copy today? So if you want to copy this white page to this gray page, you go through the processor. Basically, unfortunately, you exercise all of the bottlenecks and the data movements, as we have discussed. But again, put this in front of a 10-year-old. It'd be good to do that test and say, what would you do? Maybe that person would come up with a solution that looks like this. Why don't you just move it in memory? Right? It's just right there. So why do we go through the processor today is a good question to ask, because we're very processor-centric. Our mindset is like this. Okay, so this would be low latency if we do it in memory, low bandwidth utilization, no cache pollution, and no unwanted data movements. So I'm going to show you a very mechanism in the best case that reduces a 4 kilobyte page copy from 1,000 nanoseconds to 90 nanoseconds and 3.6 microjoules to 0.04 microjoules. And the basic idea is very simple. If you have rows in the same subarray, you first activate the source row, which brings the data into the sense amplifiers. And then you activate the destination row in quick succession, which deactivates the source row, but the data is in the sense amplifiers. And then when you activate the destination row, the data gets pushed from the sense amplifiers to the destination row, because sense amplifiers are very strong. So by doing two consecutive activations, we're exploiting the analog chart sharing capability in the bit lines and the sense amplifiers. At negligible hardware costs, you get huge benefits. Ignore the other bars. I don't have time to talk about them, but we've actually optimized the other bars because they constitute data movement across banks and across subarrays. But I've shown you within a subarray. Clearly, we move data, but we don't move the data far. It's really within the subarray itself. Okay, so that's a lot of improvement, clearly. Now, the good news is, I'm going to talk about that. You can actually do this in real DRAM chips with almost perfect reliability, as we will see. But before I say that, let me talk about theory of computation a little bit. So in circuit theory, if you activate 3 rows in DRAM, you can actually get computation done. These are 3 rows in DRAM, A, B, C. I'm showing you only 1 bit in each row and a bit line over here and a sense amplifier. Imagine that each row is 8 kilobytes. And imagine that you may have thousands of these. So you can actually do this computation on 8 million or 10 million bits at a time. If you concurrently activate these 3 rows with some primitive called triple row activation, what happens is all 3 cells share their charge with the bit line. In ideal scenarios, in ideal circuit theory, you would get, if at least 2 of these cells are charged, you get the charge state at the end, sensed at the end. If at least 2 of these cells are discharged, you get the discharge state sensed at the end. And this is a beautiful bitwise majority function. You could try changing your algorithm to actually map it to the bitwise majority function. You will not be completely successful because it's not functionally complete. What you need is functional completeness, which already exists over here. If you activate 1 row, the complement of the row is over here in the other side of the cross-coupled amplifier. So you actually already have a NOT function in memory. Now, bitwise majority is also interesting. If you take out C set to 1, you get the OR of A and B. If you take out C set to 0, you get the AND of A and B. Now we have bitwise majority, bitwise AND, bitwise OR, and bitwise NOT. bulk bitwise. Now, some applications actually are very amenable to this, and we tested a bunch of applications. Databases especially work on a lot of bitwise, bulk bitwise data. They do bitmap indices. There's a database specifically designed for maximizing bitwise operations, also web search engines. I'm not going to go through this. The paper has more detail. But we've shown significant benefits by mapping databases to this sort of bulk bitwise execution paradigm in simulation in DRAM. And the energy improvements are also commensurate. And this is one of the papers that we wrote on the topic. Now, you can make this very general purpose because you can make it very programmable. I'll very quickly go over this programmable aspect. If you think about this, user can specify any function using and or not logic. And this and or not logic, thinking like hardware. This could be convolution. This could be matrix vector multiplication. This could be anything you want. Division, continuous approximation, whatever you want over here. Polynomial evaluation. Just specify it using and or not logic. We take it, form a majority inverter graph using EDA tools that are developed by Nani Demicheli's group at EPFL. And then we optimize it and generate a sequence of DRAM commands, triple row activation, row clone, etc., some register or row allocation as well. And we store the operation as a microprogram in memory. Now, when the program calls us, let's say a matrix vector multiplication, this operation is sent to the memory controller. Memory controller executes the microprogram, a sequence of DRAM commands, and it essentially outputs the result in memory. Now, that's a lot. The paper covers a lot of it. I'll give you the key results that we obtained. Essentially, if you do this, you can implement any complex operation. Some of them take a long time, of course, but the throughput and energy efficiency and the performance we get is higher than CPUs and high-end GPUs that we've tested against. Okay, you can find more on this topic, but we have actually improved this more recently. We made it more flexible. We actually designed compilers to target this sort of substrate, and that's all described in this HPCA 2024 paper that I'm not going to talk about. Now, in the remaining time, let me quickly talk about the existing DRAM chips are quite capable. So this was all theory, let's say, and then we started testing real DRAM chips to see, can we actually see these functions in DRAM? So we developed this substrate. In this substrate, we can show that you can do row clone and true random number generation in DRAM by violating the DRAM timing parameters. You violate the timing parameter between two consecutive activates, and you can see the row clone happening between subarrays. And we actually expose this to a RISC-V core. You can download this. You can actually use it, which is beautiful. I think it was a lot of work. You can run a real application on this RISC-V core. And this real application, whenever it does a page copy, it gets shipped to the memory controller. Memory controller violates the timing parameters in DRAM to implement the page copy. DRAM doesn't change. DRAM interface doesn't change. Only the soft memory control in the FPGA changes. Of course, we add some instructions into the RISC-V to enable this. And we see significant performance benefits. These are real results from real applications, micro benchmarks. Copy and initialization throughput improves significantly. The reason these numbers are very large is because the RISC-V core we use is about 50 megahertz. It doesn't have a lot of the latency tolerance techniques that we have discussed earlier. But maybe we should be thinking about cores in a different way if we actually do memory-centric computation. Maybe the core should become much more simple going into the future. So that's PyDRAM. You can say that, okay, that's kind of cheating because you're showing us copy and initialization. More recently, in HPCA 2024, we showed that you can do a lot more. Very quick summary. Essentially, in multiple works, we've shown that you can copy one row into up to 31 other rows with more than 99.98% success rate. This is almost perfect. And remember that DRAM chips are not supporting this. We are violating the timing parameters to do the copy. We can perform the NOT operation with up to 32 output operands. We can perform up to 16 input AND, NAND, OR, and NOR operations. I'm not going to show you the copying because it's actually relatively easy to do, etc. But I'm going to show you the basic insight of the NOT operation. Actually, I've already said gave you the basic insight. If you can, this is one subarray in DRAM. This is another subarray. If you can consecutively activate the source subarray and the destination subarray, what happens is through the NOT gate, neighboring subarrays communicate with each other. So you activate the source subarray, the data in the source subarray gets sensed, and A bar appears in the destination. When you activate the destination, A bar gets stored in the destination. And we show that this is actually possible in real DRAM chips with more than 95% probability, meaning success rate. Okay, what about NAND, NOR, AND, and OR? I'll give you the basic idea. Basically, you can manipulate the bit volume voltage to express a wide variety of functions. You can implement any function, in my opinion, but we've shown some basic functions. If you look at two different subarrays that are connected through a sense amplifier over here, I'm showing you only two rows, but you can actually do more than two rows. by violating the timing parameters, you can concurrently activate all of these cells. Now, if you concurrently activate all of these cells, what happens is, based on circuit principles again, what the sense amplifier does is it compares the average voltage of cells of A and B and average voltage of cells X and Y. Now, if you're able to manipulate the voltage over here, average voltage, to let's say 3 VDD over 4, and we have a way of doing that, then what you get over here is a NAND gate. If you manipulate the average voltage over here to half VDD or 0.25 VDD, what you get over here is a NOR gate. I'm going to leave it at that. I have backup slides that talk about this, but you can imagine actually manipulating different functions. And I believe there's a lot more opportunity over here. So we tested a lot of DRAM chips using our infrastructure, and we show that you can get these functions with more than 94% success rate on average. But some operations are actually much more successful. Okay, so this is the paper. I will ask the question, what else can we do using commodity memories by violating timing parameters? I'm not suggesting people should be doing this. This is just to show that fundamentally, these chips are actually capable of things that we have not considered so far. Now, if you actually see this capability, and if you go and design the chip to be much more reliable, I believe you can do a whole lot more. Yet our mindset has not been there for many, many decades. I think maybe we should change that mindset. We should start thinking about memory as a computation device, as opposed to memory as a dumb memory device. Okay, we have shown that you can generate random numbers with very high throughput, very, let's say, low energy, etc. The basic idea, again, violating the timing parameters. You violate the timing parameter a little bit. Some cells don't have time to settle, meaning the data that you get sensed in the sense amplifier for those cells turns out to oscillate between 0 and 1. It becomes random. And if you can identify those cells that don't settle, these are random number generation cells. And you can actually get random numbers this way. This, again, across LPDDR chips, we've shown that all major manufacturers, we are able to get these random numbers. And we can have actually better mechanisms for random number generation. We have end-to-end system designs for random number generation. You can also use physical unclonable functions, etc., that I'm not going to talk about. If you want to do more complex computation, you may need to pay a little bit more. We have mechanisms for lookup table-based computation that I'm not going to talk about. I should also say that any memory is capable of this. Flash memory, we've shown very similar results. Other people have shown with real flash chips. Other people have shown with PCM, RAM chips, you can do matrix vector multiplication, etc., that I'm not going to talk about. But basically, there's a lot to do over here. Now, we cover a lot more in our modern primer that I mentioned, and we keep updating this. One of the things that we also cover is adoption. I think adoption is very important. You can build any hardware. If you don't get the software people to use it, that hardware is useless in the end. So we look at a lot of adoption issues that I'm not going to talk about because we don't have time. But a lot of these adoption issues really deal with applications, software, programming, system, security, runtime, compilation, and infrastructures. If you look at all of this, it's really the higher levels of the stack. And we really need to think about higher levels of the stack to enable this sort of new paradigm. I believe the most difficult part, in my opinion, is not the amount of resources that we dedicate. It's really this word over there, that mindset. Because if you think about how we design computers, our mindset is very processor-centric. Every decision we make in our systems today, including the theory of computation, how we actually approach the theory of computation, is processor-centric. If you don't eat away into that mindset with a memory-centric, let's minimize data movement type of mindset, I think it's going to be difficult to change everything. And in the end, we need to revisit the entire stack with this mindset. So we have works that I'm not going to talk about. We actually develop compilers to ease programmability. We develop data parallel frameworks. We develop real high-level programming frameworks to enable things. We develop tools to actually decide what to execute where. And there's more work in this area. Coherence is a tough issue. We look into that. Synchronization is an interesting issue. Virtual memory is probably the toughest issue in both processor-centric and memory-centric systems. And there's a lot of infrastructure that we develop, and I mentioned some of them, but we also develop a lot of simulators to test things, and we'd be happy to help if people are interested in using them. Now, let me conclude. I believe we want fundamentally efficient architectures. They need to be data-centric. We also want fundamentally high-performance architectures. I believe they need to be data-centric. We want fundamentally sustainable and robust architectures. I believe they also need to be data-centric. We really need to look at a paradigm where we can minimize data movement. I think I've said all of this, so I will not talk about this in more detail, but I will mention one thing over here, balanced. So when I teach digital design to 600 freshmen every year at ETH, one of the principles that I say is your system must be balanced, meaning there should be no single bottleneck. Data and control should flow nicely. And immediately after that, I teach a processor-centric system where memory is a huge bottleneck. It's the biggest bottleneck that we have. So I'm ashamed to teach that. I think we should get to a point where we teach our freshmen what is really designed in real systems, which is a balanced system where memory is not a bottleneck. So hopefully I've convinced you, and I've shown you a lot of examples that enabling computation inside and close to memory can lead to orders of magnitude improvements in terms of both performance, energy, and robustness also that I've not quantified in this work. I believe it can enable new applications and computing platforms. I strongly believe that, especially in genomics, machine learning, etc. I believe it can also enable a better understanding of nature, because I believe nature is much more data-centric than processor-centric. And who knows what else? So I think the future is really bright, but we need to do the hard work, which is research and design across the computing stack. I don't think that this machine over here is processor-centric. There's a lot over here that we don't understand yet, but I think data-centric is really built into the fundamental principles of it. Okay, with that, I will say that a lot of what we've discussed is open source. We open source almost everything. You can find all the tools that I mentioned or I didn't mention, and we'd be happy to help if people are interested in this. I'll acknowledge the funding we receive from industry generously, as well as other institutions. Most importantly, I'll mention my group. They've done the hard work that I've described over here, and you can read more about them in our newsletters. And we do hold a lot of tutorials about processing in memory. This was the last one that was held in Micro. It's all open. You can actually join on YouTube, join on Zoom. You can watch it even right now. And there's another one that's coming up in P-pop, and as well as ASPLOS next year. So if you're interested, you can participate. Thank you for bearing with me in this early morning. I'd be happy to take any questions.
Thank you for this first talk. We have time for the question.
Hi, it's a pretty investor Stratford. Thank you very much for your presentation. So a lot to take. Inject first. I think you repronounced that. You said a keyword about making our designs more reliable. Could you be more specific about that?
Yeah, that's a very good point. Basically, when I think about reliability or robustness, I think about technology scaling that I mentioned. So if you actually have a computation unit tightly coupled with the memory unit, it can overcome some of the reliability issues. For example, one of the reliability issues is refresh in DRAM. If you have a controller that is capable of understanding the characteristics of the cells and adapting its refresh rate to the cells that are less reliable, so that you can actually increase the refreshes to DRAM for less reliable cells and reduce the refreshes for more reliable cells, I believe you can make your system more reliable in cases where you may have missed the refresh rate for less reliable cells, and also efficient at the same time in cases where the refresh rate that you decide is actually too much for more reliable cells. So that's one example. If you actually have a controller co-designed together with your memory, you can play a lot of these tricks that can make things more reliable.
Questions? Thank you for your talk. I have a question about the processing memory that you've done in DRAM. Basically multiple accessing in DRAM. Does that expose you to problems that are similar to the RowHammer model? And that's a question. To the recent improvements in memory, put values in your RowHammer model prevent you from doing those things?
Yeah, those are two excellent questions. The answer to the first one, yes. If you actually activate more rows, you induce more noise. And this actually exacerbates some of the reliability problems, including RowHammer. And we're actually studying this effect. We're developing solutions. The answer to the second one, which is also a very good question, is I think it remains to be seen, depending on what will be implemented in real DRAM chips and how restrictive it will be to the interface. But based on what we have studied, the per row activation counters, for example, I don't believe they should really hamper multiple row activation type of computation, because hopefully a lot of that computation will not be essentially having a RowHammer type of access pattern. But again, this needs to be studied experimentally.
Always exciting. So, picture is Apple chip, okay, and left and right, DRAMs, they're connected with chip, let's say the connection. So, okay, the DRAM pieces are real, that's size. So, I would like to have some comments to say, make the project chip, how will it influence memory because now the chip the connector are closed, let's say.
Yeah, so thank you for the comments. I think chiplets are very interesting because that can enable heterogeneity in the chiplet subsystem also. So in my opinion, chiplets should be used not just to scale computation, but also mix and match different type of components so that they can be interconnected nicely. So some of the chiplets can be more memory-centric, for example. Some of the chiplets can be processor-centric, and can enable a system that's kind of envisioned earlier, like the Google, like the system, Mensa system, where we wanted to accelerate machine learning in a heterogeneous way. So in my opinion, there's a lot of opportunity. And hopefully we won't waste that opportunity by just making things processor-centric.
Oh.
Yes. Thank you.
Yes, please. Thank you for the nice presentation. So you have implemented different applications using memory-centric computing like graph processing, deep neural. So have you tried the security algorithms? Because there are some algorithms which are computational intensive. So a lot of work is done on FPGA and ASIC.
Yes.
Like there is post-quantum crypto nowadays. So have you tried the algorithms and what are is it feasible to design specific memory architectures for these security algorithms?
Yeah, thanks. We have tried some of them, like we've looked at homomorphic encryption, for example, and we see significant benefits when the underlying processing in memory architecture can do addition, homomorphic addition and multiplication, for example, and you can customize it. Other people have also shown this actually, not just us. So there's work in that area, but I believe it needs to be examined more end-to-end, like a full application basis. If you can offload full security critical processing to the memory side and not move anything to the processor, fundamentally, you can actually improve security properties also. But the short answer to your question is yes, and there's a lot of benefit to be gained, but I believe there's more benefit to be gained if we actually do more research.
One more question is how this idea will move to the quantum computing domain?
Yeah.
Computed memory, right? The quantum computing.
So that's a great question that I probably cannot answer at the moment with my current knowledge. In my opinion, based on what I understand about quantum computing, it's very difficult to have quantum computing an impact on the memory side the way it's designed today. So quantum computing is an accelerator that will accelerate some computations. But I don't think it is a good answer for memory today, meaning it has to be coupled with a lot of the memory technologies that we develop today, unless people actually really seriously start inventing quantum memories in some way. There are some works in that area, but I don't think they're as mature. I believe these ideas are all applicable to quantum computing. Quantum computing can accelerate some processing tasks, but then memory-bound tasks may not be very well accelerated by quantum accelerators.
Thank you. Thank you for your nice presentation. You mentioned the problem of memory software, and I would like to see if you have thought about a roadmap to convince software people to adopt these proposed technologies.
Yeah, that's a good question. I think maybe I wouldn't call it a roadmap, but essentially, if you can meet if you can minimize the effort on the software side, things can be adopted much more easily. For example, if the software folks don't change anything that they do, if you can accelerate things underneath through compilation techniques, that's great, I think. And we have been looking at that, and you would get some benefits if you actually do that. Software folks don't change anything, you do compilation. But the benefits, if you want higher benefits, you need to change some things. So you need to change the programming model using high-level frameworks. And the next thing that people could do is maybe change the framework a little bit so that they can program using the high-level frameworks that we've developed to do processing in memory. So ideally, there should be a step-by-step process where nothing changes and you gain benefit, but the benefit may not be enough. But over time, you discover the benefits more and you start changing things. It's also hard to predict, I think. One of the issues we have with processing in memory is hardware is not as mature. If you go back like 30 years or so, 20 years or so, when GPUs were coming out, there were GPUs in every machine. And some programming folks said that, oh, let's use them for our computation. And over time, people have developed things, and some big company came up with a relatively not hard to program model that actually captured everybody's attention. So I think sometimes it may be difficult to predict, but we need to find the right balance.
Also, thinking of the case, let's say, modern computer with an AMD chip, do you think it's possible to change the operating system and get the results? If so, good perception that makes
let me clarify. What kind of results are you looking at? Like the ones that I showed where you would violate the timing parameters and do computation? So certainly it's possible to do. So if you design a processor chip, and if you design a memory controller, there's nothing that could prevent you from changing the memory controller so that you can do these operations. That's essentially what we did with the IEDM prototype that I mentioned. We didn't do it on an AMD chip because we don't have access to the proprietary memory controller, of course. But we do have access to the FPGA memory controller. It's a soft memory controller. So it's possible to do. It requires changes to the hardware still. It requires this violating the timing parameters that normally memory controllers don't do. It's not a huge change. I think it's possible. And I think it'd be great if hardware companies do that change so that we can test some of these functions more and more. Now, that said, this will still be a testing or prototyping platform. I don't expect anyone to use it immediately because there are issues like we discussed. You don't get 100% robustness, right? Robustness is an issue in these operations. You get 94%, 99.98% if you do copying. So there are some things you could do. Some applications can take advantage of it. It'd be great, but it's probably still far away from what we would ideally want, but it could be a step.
Thank you. And I will ask the last question because, yeah,
Sure.
Minutes. Thank you again for this talk. My question is, okay, you mentioned lots of benefits of memory and the gains that you bring in terms of energy efficiency, also principal performances. But in your opinion, are there some limitations of the processing in memory approach, and what type of application, what type of processing are not really this type of part?
Yeah, that's a great question. I mean, certainly there are limitations, right? Especially the adoption. All of the adoption issues that I mentioned are some of the current limitations that could be solved over time. But certainly not everything that you do should be done near data. There's some. We actually had a work called DAMU, which classifies bottlenecks of programs into 6 things. And one of the bottlenecks is really compute-centric, meaning you have so much computation and you have little data that you're working on, or you have a lot of data reuse that you just want to build the fastest compute-centric processor possible. And there are parts of programs that are like that. And for those parts, I'm not suggesting we should use processing in memory. For those parts, you build a very specialized accelerator or very specialized general purpose processor, whatever it is, that is extremely efficient at that computation, but that doesn't have all of those hierarchies that we're currently adding to our systems to overcome the data bottlenecks. So yes, I think we need to classify the needs of different parts of the programs and appropriately accelerate them at different parts of the system. And the answer is not going to be processing in memory for every part of the program.
Thank you. Let's thank you again.
Thank you.
Thank you. That was all good to you.
Oh, thank you.
It's coming.
Oh,
We're really honored
oh,
to have you with us.
thank you very much.
And yeah, you have also some
Oh.
local specialists.
Thank you. I
Thank you.
appreciate it. Thank you.